Get started.
Okay. Respected senior members of Indian Nuclear Society and friends, it gives me a great pleasure in welcoming you all to today's webinar. This is one of the very important activity of INS, wherein we invite eminent speakers in important positions and accomplishments to speak on our platform. The aim is to bring to the knowledge of our members about the important development in nuclear science and engineering, climate change, societal benefits from nuclear science, energy, and nuclear defense and security system. In the past, we also had the opportunity of hearing experts from outside atomic energy. Our 11th webinar talk was given by Professor R. Srikanth on the role of nuclear power in India's green energy transition, challenges and way forward. In his talk, he also had mentioned about India's plan of constructing efficient thermal plants. Today, we have with us Sri Neeraj Sinha, Senior Advisor in NITI Aayog and heading Science and Technology and Digital Communication. He is going to talk to us on indigenous development of advanced ultra supercritical technology for thermal power generation in India. Sir, on behalf of Indian Nuclear Society and on behalf of INS Webinar Subcommittee, I welcome you on our Zoom platform. It is our great honor to welcome you and listen to your technologically advanced challenges. Sri Neeraj Sinha is a multifaceted technocrat with a wide range of technical know-how picked up during his tenure in PSA, that is Principal Scientific Advisor to Government of India in his office, and now with NITI Aayog. He is a man with mission to take forward the technological inventions to commercial product. The supercritical based thermal power plants are one of the India's dream project jointly developed by Power Industry and Research Institute. IGCAR as a research institute has played a key contribution in terms of material development for this project. And NTPC and BHEL are the industrial partners. It is an efficient thermal plant which is to a large extent environmentally friendly in terms of carbon emission. Sri Neeraj Sinha is going to talk to us more on all this. So before we introduce the speaker to our members, I will request Sri Mehtaji, who is our President of Indian Nuclear Society, to make his opening remark.
Welcome, Dr. Sinha, to the Indian Nuclear Society seminar web series. Your talk on the advanced ultra supercritical technology for thermal power station generation is a very important step toward the optimal utilization of the resources. At the same time, your views, being a senior advisor in the NITI Aayog, will give us a background as to how the nuclear energy can fit in the whole program and how that can be contribution from our side. Of course, all kinds of energy is required to meet our demand, at the same time to reduce the carbon dioxide burden on the atmosphere. So we have to sort of synthesize the total program in such a way that we meet our objectives and international commitment. So welcome you again and welcome to all the members here.
Thank you so much. Thank you.
Thank you, Ramarao. Please stand.
Yeah.
So, Ramarao, shall I read the profile?
Yes.
Yeah. So, good afternoon to everyone. It is my pleasure. Am I audible?
Yeah.
Yes.
It's my pleasure to introduce Sri Neeraj Sinha to this gathering. Sri Neeraj Sinha graduated with distinction in the year 1987 from the REC College, Surat, in mechanical engineering. He joined the Government of India Department of Non-Conventional Energy Sources, now the Ministry of New and Renewable Energy, in the year 1989, working on several new and upcoming technologies during his 9-year stint, such as electric vehicles, alternate fuel vehicles, hydrogen energy, and geothermal energy, as well as biomass-based power generation. He joined the office of the Principal Scientific Advisor to the Government of India in December 2001 and after working there for more than 17 years, has recently joined on deputation the Niti Aayog as advisor, science and technology. In the office of the principal advisor to the Government of India, he has been involved in a wide cross-section of scientific activities. To name a few: oil spill management, underground coal gasification, bulk encryption, explosive detection, integrated gasification, combined cycle for coal-based power generation, night vision devices, setting up of a national knowledge network, multi-purpose national identity cards, climate change, clean coal for carbon technologies, national photonics initiative, medical sterilization, drugs and diagnostic centers for spurious and substandard drugs, development of advanced ultra supercritical technology for coal-based power generation, and the development of advanced machine tools. So his profile is really broad-based, and it will be really enlightening to hear from him. He has also actively contributed to the preparation of National Action Plan on Climate Change, which was released by the Prime Minister of India on the 30th of June 2008. He has submitted his thesis on 3 nitrides for energy-related photovoltaic and LED applications for the award of the PhD degree. He has co-authored more than 32 scientific papers on this subject. In the science and technology vertical of the Niti Aayog, he has actively contributed thus far to the continued implementation of the Atal Innovation Mission and has also guided actively the preparation of the following: the memorandum for the Expenditure Finance Committee on the use of methanol as an alternate fuel, and the draft cabinet note for the launch of a new program for facilitating the return of the best-in-class scientists from abroad to India. He is a fellow of the Institute of Engineers and a life member of the Administrative Staff College of India, Hyderabad. He has been awarded the Medal for Materials of the Materials Research Society of India, MRSI, in February 2018. So with this introduction, it's now my pleasure and privilege to invite him to kindly commence his presentation. Mr. Sinha, please.
Yes, thank you so much, Dr. Ramurthy. Thank you for the very detailed introduction, and a big thank you to the Indian Nuclear Society for having considered this subject worthy of being shared with senior colleagues like you and with all other people who have already joined online. A very warm welcome to them on my personal behalf as well, and on behalf of the Niti Aayog, and of course on behalf of the Principal Scientific Advisor's Office, where most of this work was done. And of course, a warm word of gratitude to the President of the Indian Nuclear Society, Dr. S.K. Mehta, and to the Secretary, Dr. S.K. Malhotra, and of course to Dr. A. Ramarao, who has facilitated my joining this webinar series today after quite a few changes here and there. But thanks to all of you for having me here, and a big thank you on behalf of all those people who have made this technology development possible. There are a score of scientists in BHEL, engineers in NTPC, and in the Indira Gandhi Center for Atomic Research, scientists and engineers both. So I'll just, with this brief background, I'll just go on to the first slide. And I believe I have about 45 minutes, Dr. Ramarao.
Yeah, please go ahead,
Okay.
sir.
Okay. So now, just to give a brief background on how all this started, it has a history. Now, history is not science, but it is important for us to realize how we were able to get everything together in a fairly short period of time. So quite some time ago, in October 2009, the PSA's office, under the stewardship of Dr. R. Chidambaram, the then Principal Scientific Advisor to the Government of India, had organized a series of meetings. And all these meetings were actually nucleated by Mr. Shyam Saran, who was the then Special Envoy of the Prime Minister on climate change issues. And he had requested Dr. Chidambaram to convene these meetings, knowing that clean coal carbon technologies is a very broad subject. It is handled by myriad ministries and departments, myriad public sector undertakings, and several stakeholders in the private sector, in the academia, in the government lab system, and of course, in the all our scientists and researchers. A lot of people are working on this area. So he thought that it would be best possible to stitch those efforts together through Dr. Chidambam. So Dr. Chidambam conducted these series of meetings. Dr. V.K. Saraswat was a very active participant in all these meetings. At that time, he was the secretary in the Department of Defense Research and Development. And of course, he's now the member in charge of science and technology in the Niti Aayog. And other than Mr. Shyam Saran and Dr. Chidambam, Dr. Baldev Raj, the late Dr. Baldev Raj, played a sterling role. And it was he who led this entire effort from the front. We all deeply miss him, of course, but then I think the best ode to his memory would be to realize this technology into an actual thermal power plant. And of course, the other two people who played a very active role, and one of them is continuing to play an active role even today, is the first is Mr. Chandan Roy, who used to be Director of Operations in the NTPC. And even after retiring, he continued working with us on this technology development from 2011 onwards. And the second and the most important person in this entire chain is Mr. S.C. Chetal, former director in the Gandhi Center for Atomic Research. And now he joined the PSC's office as a consultant, and now he's a consultant in the Bharat Heavy Electricals Limited. So what we did was we got the academia, the industry, and of course the government labs and the government ministries and departments to come on a single platform and discuss how best we could launch a 9th national mission on clean coal carbon technologies. As you might remember, the National Action Plan on Climate Change had 8 national missions, but clean coal carbon technology was not addressed there. So Mr. Shamsan rightly pointed this out, this lacuna to us, and then we kind of started talking on these 3 submissions. One was the integrated gasification combined cycle. The other was the development of advanced ultra supercritical technology for thermal power plants. And the third was carbon capture and sequestration. So of all these 3 submissions that we thought of, it was a collective wisdom that made us decide that the AUSC technology development work was best poised, and there was enough expertise already available in the country to start this very ambitious project. Now, I don't need to tell this gathering that India had not, and even today does not, manufacture even subcritical thermal power sets. I mean, subcritical turbines are not manufactured in India. They are all imported. They are all made in India, of course, but based on imported technology and under license from either GE or Siemens or Alstom. Now, of course, GE and Alstom are together. So now it's either from GE or Siemens. So it was a tall order when we did not know how to design a turbine, even at subcritical parameters of steam. We were talking about taking a quantum jump from subcritical straight to advanced ultra supercritical, bypassing the other well-known chains, which are, of course, supercritical and then ultra supercritical. So advanced ultra supercritical parameters were set as 710 degrees Celsius temperature and of the steam, 710 degrees Celsius reheat steam temperature, 720 degrees Celsius reheat steam temperature, and the pressure was 300 bar. So when we thought of doing such an ambitious thing, we thought that it would be best to take the blessings of the then Prime Minister, which we did on the 17th of November. The presentation then was made by Dr. Baldev Raj. And of course, the then Planning Commission was represented by the member industry, all secretaries, all CMDs, and Dr. Chidambam, of course, was present along with Mr. Shamsala. So in that meeting, the Prime Minister consented, and it was decided that since BHEL will end up doing most of the R&D, in association, of course, with the Indira Gandhi Center for Atomic Research, we thought that the R&D work should be steered by the Department of Heavy Industry, because the BHEL administratively reports to the DHI. And we tasked the DHI to prepare the cabinet note for the R&D work, for developing the AUSC technology in the country. And we also said that once the R&D work is over, the Ministry of Power will take over, because NTPC will then be the utility that sets up this plant. So we set up a consortium of IGCAL, BHEL, and NTPC, and there was a proper MOU that was signed in August 2010. And then we laid down a few parameters. Of course, a lot of things were unknown at that time, but we laid down a few parameters, a few areas of collaboration in that MOU, which is still around. And in March 2011, commencing March 2011, we especially Dr. Baldev Raj felt so, and then Dr. Chidambam agreed with him that while the MOU is signed, and MOUs are signed left, right, and center in the country, by the way, it was important for us to ensure that the three organizations start work. And for starting work, we need money. And money from the government of India was not obviously going to come immediately because a cabinet note takes time for approval. And based on Dr. Baldeva's wide experience, he had suggested that the right size of or right capacity of power plant would be 800 megawatt electrical to be set up based on this technology. And pending that, he said that let us start some pre-project R&D activities between these three consortium partners, so that not only do they continue to work on the technology development, but they also remain together. So we identified 10 different areas. In the subsequent slides, I'll be showing, and these areas were identified based on inputs from the consortium partners, obviously, because the PS's office did not dictate or did not say anything here. We totally went by the consortium's own judgment. And those R&D projects were funded by the PS's office for about 5 to 10 crores of rupees per project, which was not a big money, but it was not a small money either in those days, about 11 years ago. So we were able to develop and demonstrate quite a few critical technologies, which then added on to the entire technology development happening just about a year and a half ago. So as I was just saying, the CCA approval, the Cabinet Committee on Economic Affairs approval took a long time. And there were a lot of behind the scenes activities that was done by the PS's office to ensure that the CCA approves this project. So it was on the 10th of August in 2016, more than 5 years after we started the pre-project R&D activities, that the CCA approved this project at a total cost of 1,554 crores for the duration of 2.5 years starting April 2017. And this 1,554 crores included 554 crores by the consortium, I mean by NTPC, BHEL and IGCAR. IGCAR's participation, now as we all know, Department of Energy is not supposed to, by mandate, dabble in thermal power, that is coal-based power generation. So, but the leaders then in the DAE, Dr. Banerjee, he's no more with us, of course. I mean, so we have lost so many people, but anyway, Dr. Banerjee and then Dr. A.K. Bhaduri, who also left us just about a month ago. He was the director of the MMG group in the IGCAR, Materials and Metallurgy group in the IGCAR at that time. So they kind of put together these project proposals in association with the NTPC and the BHEL, because they brought the materials expertise to the consortium. While BHEL has some resident knowledge in design of boilers, I mean, of course, they have tremendous knowledge now. Over the years, Tichy manufactures all kinds of boilers for various kinds of customers, but none of them had any materials technology idea. So the IGCAR played a stirring role here, and they were allowed to participate under the garb of doing R&D for high temperature materials research. And the DAE sanctioned a substantial amount of, I don't remember the figure now, it was I think 234 crores for doing this job. And as I was saying, the initial estimate was that the R&D would take 2.5 years and the erection and commissioning of the plant would take 4.5 years. So we were looking at 7.5 years from the day of sanction. The day of sanction, as we know, is August 2016. Now, this is a chart which Dr. Baldevdad had put together. We keep showing it all the time. So subcritical sets were being installed routinely in the country that day, in those days. So the size typically is a 500 megawatt electrical set. The steam pressure is 170 bar and the steam temperature is 537 is a steam temperature, 565 is the reheat steam temperature. Efficiency is as low as 38.5 and the specific consumption of coal is 560 kg per megawatt hour. Now, as we go up the ladder, supercritical, the steam pressure increases, the steam temperature increases. Consequently, the efficiency also increases. And of course, the coal consumption goes down. Now, finally, the row in the red color is what we targeted. Around 310 bar of steam pressure, 800 megawatt electrical was the unit size. 710, as I said, was the entry temperature. 720 was the reheat temperature. And 46 degrees Celsius. Now, this was 46%, sorry. This was the efficiency that was calculated to be possible. Of course, there were a lot of engineers who opposed this figure at that time, but then they all gradually came in line. And the coal consumption comes down to 467. Now, the footnote says for the 800 megawatt electrical AUSC, the reduction in coal consumption is about 5 lakh tons per year, which is really substantive when compared to a supercritical boiler. Now, these are some of the materials issues that we identified 11 years ago. That is when, or rather 12 years, almost 12 years ago now, in August 2010. The challenges were the design of the boiler, the design of the boiler tubes, the high pressure steam piping and the headers of the boilers, the superheater tubing, and of course the water valve tubing. Now the photograph here shows water valve corrosion in the set that was being installed at that time, and we had to fight this problem as well. So, and this of course is courtesy Dr. Baldev. Now this is the chart he drew, giving a broad framework of cooperation. Now, IGCAR, as I just said, was made in charge of materials design, materials development, materials testing. And of course, all this work was supposed to feed into the design of the power cycle equipment, the systems engineering, the design of the steam cycle, and the test loops by the BHEL. And it was supposed to obviously feed into the NTPC's work on the detailed project report preparation, on project management, and on O&M. So this is the synergy that we had thought should be there. And I'm glad to share with all of you that this did happen. Let me also share with you that BHEL and NTPC had never until then worked together for such a long period of time on any kind of technology development. If I remember correctly, BHEL was set up in the 50s, NTPC came in the 70s. So they have coexisted for almost 50 years now, 5 decades. And they had not cooperated on any technology development for this longer period of time and for such a challenging job. So this was a major achievement. We were as a team, and this really helped us to achieve what we did. Now, these, as I just mentioned a little while ago, these are the pre-project R&D activities that the PS's office had sanctioned starting on the 28th of March. I will just touch upon the first one. Now, here we involved the Mishra Dhatu Nigam Limited in Hyderabad, and we involved the nuclear fuel complex again in Hyderabad. The Midhani was tasked to prepare a nickel alloy 617M, and a stainless steel, which was Super 304H copper, Super 304HCU as we used to call it. And they did it wonderfully. They made it. They made the material in-house through this project. The materials were tested, the tubes were drawn by NFC, and those tubes were tested to be better than the imported versions, which were coming from Spain and other parts of Europe. So this was way back in March 2011. The project lasted for about, all these projects typically were for 3 to 3.5 years. Typically, some might have finished a little earlier, but most of them went to 3.5 years. For some of them also went to 4 years. Now, the others, of course, are equally important, but I'll not, for paucity of time, go into the details. But the second one was equally far-sighted, because here we were talking about turbine blades being made in a totally new material, which is difficult to machine, alloy 617M. And through this project, we were able to demonstrate that BHEL had the capacity to machine the turbine blades from a block of alloy 617M. But of course, the machining time per blade was about 4 hours. So we obviously wanted to reduce that with time, but this was a big shot in the arm for all of us that we were capable of producing these turbine blades in India, indigenously. Now, the third challenge there was the dissimilar metal weld joints, on which IGCAR did a sterling job. They were able to demonstrate in 1:1 sizes the dissimilar metal joining of alloy 617M with 10% chromium steel. And this was for both the turbine casing and the turbine rotor, for both of them. Now, why did we go for this, by the way? We went for this, I mean, we could as well have had a turbine casing and a turbine rotor with the nickel alloy and not worry about 10% chrome. But then that would have been very, very costly. Nickel, as we all know, is a very costly material. And that is what added to the cost of the project. Even today, it adds to the cost of the project. So we wanted to reduce to the extent possible by design, that is, the use of alloy 617M in the construction of the turbine. Now I'll just run through the others. So the last of these projects was sanctioned on the 20th of February 2017. And this was a high velocity oxygen fueled spraying of the chromium nickel chromium coating on grade T91 boiler tubes. And this was done by the Bhopal unit of the BHEL, of course, on the full technological support of the IGCAR. Now, as I was just saying, all these 10 activities were targeted to, number one, gainfully use the lead time from the date of the signing of the MOU up to the actual sanction of project, so that we could actually keep working and not, disintegrate after the signing of the MOU. And of course, we kept the consumption together, very actively together through these Preproject R&D activities. Now, just to remember fondly all those seniors who had contributed so actively and so selflessly their very valuable time on the development of the technology by guiding and reviewing the project team. So Dr. P. Rama Rao is the first person I should give my regards and give my obeisance to. He brought the PLMC, we used to call it a common project review and monitoring committee. And this was only, by the way, for those 10 Preproject R&D activities, not for the main project. The main project had a different review mechanism altogether. So of course, Dr. Rama Rao led the committee with Mr. Chetal as a member, and the CMD of Midhani as another member. Dr. G.K. Day, at that time when this committee was formed, he was the head of the Materials Science Division. Then he became the group director of the Materials Group, and now, of course, he is superannuated. So this says his designation in those days. And Dr. Choksi, professor in the Department of Material Engineering, also contributed heavily, and I was the member secretary to the committee. Now, Dr. Rama Rao realized in the very first couple of meetings of the PLMC that this work was going to be difficult, not because of the technological challenge alone, but because of the very tough task of bringing BHEL and NPCC together. Now we could see between them, although both are equally valuable to the country and both are Maharatnas, we could see between them the buyer-seller relationship. I mean, the NTPC buyers and the BHEL cells. So it kind of became a little difficult for us to, digest, because this is not the way we do research. No one does research this way, by the way. Everyone is supposed to be an equal partner. But gradually they came around and they were able to really, contribute in a fairly short period of time, whatever they were tasked with. Now, so what Dr. Rama Rao did was, he knew that he could not meet very frequently because he had some constraint on travel in those days also. We had to meet in Hyderabad since he's Hyderabad based. So he formed a subcommittee. We called it the subcommittee 2. There was a subcommittee 1 under the chairmanship of Dr. G.K. Day, which was supposed to submit a report on the materials development, which they did. So the subcommittee 2 was chaired by Mr. Chandan Roy, but then, as I was saying, he left us in 2016 itself. And then Mr. Chetal took over. He was the co-chairman earlier, then he became the chairman. The director of engineering R&D of BHEL and Mr. D.K. Dubey is now retired. He used to be the regional executive director of NTPC Limited in Hyderabad. So they were representing the two main partners. And of course, the PS's office was supposed to be the secretariat to this committee. Now, of course, there were some achievements we asked the subcommittee to work for, and they did that. They created a comprehensive report on the materials selection for the 800 megawatt electrical demonstration project, and they also created a project design memorandum for the same project. And all this was done way back in, if I remember correctly, 2013-14, in that year. In fact, 2013 January. Now, I'll come to the main project now, and then I'll go on to the achievements that were made. The main project, once it was sanctioned in August 2016 for implementation beginning from April 2017 at a prospective date. So we had, I mean, the entire cabinet note was drafted by us means PS's office, and the then CMD BHEL, Mr. BP Rao, and of course, Mr. D.K. Dubey and Mr. Chandan Roy from the NTPC, and Mr. Chetal from the IGCAR. So we kind of devised a 3-level or a 3-tier system to monitor these projects. The first tier, I'm showing those 3 tiers here, of course. The first tier was the project executing committee or the execution committee, which was at the unit level. Let us say BHEL Hyderabad is implementing a project. The ED in charge of that unit chaired this committee with representation from the other 2 partners, and vice versa. If it was IGCA, then Director IGCA nominated a chairman for the project execution committee, and the other 2 partners took over as members. And that was the first level, of course. The second level was the mission directorate. Now, the mission directorate was set up with Mr. S.C. Chetal, who was selected through a diligent selection process, and the selection committee at that time was chaired by Dr. Chidamam. So he was selected to be the mission director, and the mission directorate was funded by the Department of Heavy Industry, because the cabinet approval, when it came, the money flowed into the DHI. The contribution from the Government of India flowed into the Department of Heavy Industry, and from there it flowed into BHEL, NPCC, and IGCA, as the case may be. So they funded the setting up of this mission directorate in Noida, and the mission directorate was functioning until March 2021. That is when we wound up, after we completed the entire work. And of course, I just mentioned the PRMC, but this was a different PRMC, not the same as Dr. Ramarao. And finally, there was an overarching committee that was constituted at the highest level. Dr. Chidamam, as PSA, was the chairman. And we had the secretaries of Department of Heavy Industry, Ministry of Power, and Atomic Energy, Secretary DAE, that is, and a senior representative from the Department of Expenditure, and of course the CMD BHEL, CMD NTPC as members. And the mission director was the member secretary to this committee. Now, what were the broad activities? Now, I've tried to summarize this. The activities were huge, but what came to my mind was these 6 bullets, and I checked with Mr. Chetal whether there was anything else to be added, but he agreed that this kind of covered everything. And in fact, he drove the entire R&D through the mission directorate, and frankly, we can't thank him enough for doing that. Now, the first bullet is the design of components impacted by the AUSC stream parameters and the design review of the key components by foreign experts. Now, what I mean here is we had, after the design of the boiler and the design of the steam turbine were completed, respective, boiler was by, of course, BHEL Trichy, and the steam turbine was by BHEL Haridwar. So after this was done, we had got both these design documents validated by foreign organizations. The boiler design was validated by the EPRI of the US, and the turbine design was validated by the Siemens. Now, it was quite an uphill task to get BHEL to agree, and there were a lot of concerns on IP, and because even leave alone Siemens, no country in the world has actually designed and operated anything at advanced ultra supercritical parameters. The reasons could be many. It is not that they lack the technical expertise. It is likely that governments the world over, especially in the Western hemisphere of this world, are gradually receding from coal as a source of power and going into alternate sources of energy. So that could be the reason. I don't know what the real reason is, but Siemens had not designed this kind of a turbine ever. So the review was successfully done by both these organizations, EPRI for boiler and Siemens for the turbine. And design of steam turbine, as I said, has been undertaken for the first time in the country for any parameter of steam, leave alone advanced ultra supercritical parameter. Then there was indigenous production of materials for the boiler tube, which I just mentioned, the wall forgings and the turbine castings in nickel-based alloys. And then there was the manufacturing technology for the AUSC boiler and the AUSC turbine. The welded construction was the biometallic welded construction, which I just mentioned. And establishing of engineering facilities for the corrosion evaluation of boiler tubes and the design of the steam turbine rotor. Now, for the corrosion evaluation of boiler tubes, we had set up a full-fledged turbine, we had set up a test loop this was in the Dadri unit of the NTPC. And this was done when the project was still underway. And this was in the year 2019. In fact, February 2019, when the test loop was commissioned in Dadri. And all parameters were studied. It was established by experimentation that in a live power plant, we were able to, of course, the boiler, the temperature of steam was not as high as advanced. The unit in Dadri is only, to the best of my knowledge, a supercritical unit. But we pressurized and we rose the temperature of steam to the levels we wanted, and then we passed them through the boiler tubes. And then we studied the corrosion, we studied the material loss, and all results were positive and spoke volumes of the fact that the materials that had been selected very diligently had been tested for being capable of withstanding those high temperatures and pressures. So, and finally, the last bullet says creating national assets for materials evaluation and testing in academic and R&D institutions. Now, this was, other than the main R&D project, we obviously, I mean, not everything could be done by the consortium. Not everything could be done by BHEL and IGCAR. So what they did was, on our advice, they, from the money they obtained from the Department of Heavy Industry, they formulated project proposals to be implemented by the various academic institutes in partnership with industry. For example, there were projects done by IIT Madras, there were projects done by CSAR labs, and in each of these, BHEL and NPCC had actively participated. I mean, there's quite a lot of projects. I don't have the full list here. I didn't show it on purpose, but there were quite a lot of projects that were implemented at the back end. Now, India's need for AUSC, this is very obvious. I will not spend time on this. As I was just saying, the coal consumption comes down fairly substantially, and emission also comes down substantially, and the efficiency goes up. 46% is a quantum jump again, because the advanced, or rather the supercritical sets and the ultra supercritical sets that are currently being installed by NTPC based on imported technology have a maximum efficiency of 41.5%. I'm talking about the overall thermal cycle. Maximum efficiency of 41.5%. And we are talking about 46% here. So now it appeared at that time, and it, as far as I'm concerned, even today, we can fulfill our obligations to the world. Not that we will stop burning coal. We should continue to burn coal because coal is our mainstay. And the US continued to drill for shale gas once they discovered it, I think around 15 years ago, without worrying for the environment. They exploited it to the extent possible because they were saying that this is our resource and we are going to use it the way we want. I don't know why we are shying away from using coal. I agree that we should behave responsibly. We cannot pollute the environment because our future generations will be at risk. Why future when the current generation will be at risk? But let us burn coal as efficiently and as responsibly as possible. So when we talk about it, thermal efficiency of 46%, you obviously talk about reduced emissions, and you obviously talk about reduced coal consumption as well. So, and the third and the most important point is, other than the reduction in, other than the benefit to the environment and the rise in efficiency, we are also looking at the possibility of India building a industry through BHEL and through its all auxiliary companies, a world leader in AUSC technology development. We could end up supplying AUSC boilers, AUSC turbines, AUSC piping, AUSC valves to at least our neighbors for the time being, and maybe to the rest of Asia as well. Now, coal to remain integral to India's energy security, I just said that. Now, India has a great push for renewable energy, as we all know. We are predicting of a 40 to 45% energy mix by 2027. However, the cyclic behavior of RE, that is renewable energy, again calls for baseline capacity of coal-based generation for stability. That is number one. Number two, now, when we made this slide, the COP26 had not happened until then. So now we know that the Prime Minister has declared that India will be carbon neutral by the year 2070. And not by any yardstick of imagination, engineering calculation, engineering design, can we achieve that target based on renewable energy alone. Nuclear energy is going to be a big role. That is, I mean, there is a parallel activity being done by the NITI Aayog under the chairmanship of the Vice Chairman NITI Aayog on the development of small modular nuclear reactors. And the report of that committee will come out shortly. And as the president of the Indian Nuclear Society also said, all forms of energy are important. We need to see how do we use them and what is the energy mix that we come up with. So coal burning in a way in which we are able to reduce emissions to the extent possible should remain a part of the energy mix. we cannot do it with coal. And I remember the PM making a similar statement in COP26 when I was in Glasgow. Now, this is, of course, I've been telling about this. So this also I have said. Now, these were the areas of the work identified. The first two bullets I've already spoken about. The manufacturing technology also I've spoken about, of the turbine rotor and casing with new materials. Alloy 617M, the M is missing there, alloy 625M. Now, production of alloy 625M casting for turbine inner casing, manufacturing of technology of the materials to be used in the boiler, material data for the design of various components, both for lab testing and also through open literature was to be collected. And the fireside corrosion testing I've just said. And of course, the other major thing that was done was, now these two items were funded by the DST. That talks about the cooperation we got for almost every quarter in the government of India. The bullets, the second last and the third last bullets were funded. I mean, the work there was funded by the DST to the tune of about 100 crores. And this was thanks to Dr. Baldevraj when he saw that despite our best efforts, the entire R&D work was not seeing the light of day because of the cabinet approval not coming through. He had spoken to the then Secretary DST, and the Secretary DST had initially agreed for a smaller sum. But when he understood the enormity of the work that was going on, he very generously gave 100 crores for this work. So this turbine rotor test facility has come up already. It is functioning now. And it is also a first of its kind in country, and it could be the world over, but I'm not very sure about the world over part. It could be where we are actually planning to test at actual RPMs the AUSC rotor as and when it is made. Pending that, the test facility has also been operated with a casing made of steel, and this has come up in the corporate R&D division of the BHEL in Hyderabad. But let me also say that this facility was not made indigenously. This was largely imported. A few of the items were indigenous. Engineers of BHEL were involved in setting it up in Asipuram, but largely it was imported. Now, these are the material selection basics. We know that adequate mechanical strength at design temperature, high tensile and clip properties, adequate low cycle and high cycle fatigue resistance, reduce embrittlement, etc. Were to be studied. Corrosion resistance was studied not only from the scaling point of view, but also from the water chemistry point of view. Weldability and manufacturability of all the components was established. Physical properties, that is higher thermal conductivity, higher thermal diffusivity, and other properties like low thermal expansion coefficient were all measured through experimental work. Availability of materials in required sizes was ensured, and overall economics, of course, was an important part. Now, this talks about a comparison of T91, which is the normal boiler tube that is used currently in supercritical and ultra supercritical sets, with the high temperature materials. Now, 740 is something we have not used so far. We might ultimately do that because 740 is Inconel 740 is patented by the US, by some company in the US, and we didn't want to touch that because the patent is still live. So 617, 625 are the materials we selected. Sanicro we selected as we matured doing the R&D work, and E911 also came up after we matured a little. And all this was Sanicro and E911 were primarily brought in to reduce 625 and 617 to the extent possible, which were of the costlier the nickel variety. Now, we also said that we need to give economics an important consideration because ultimately, and of course, this is not at the cost of structural integrity, of course, but ultimately, all these plants should be commercial viable and should be multiplied in numbers over the years. So we didn't want to create something which cannot be sold to customers or which cannot be established at a techno-economic level. So now, as I said, the reduction in usage of expensive nickel-based alloys, as just mentioned, the welded rotor and casing, we brought in E911 and we brought in G911 in place of Inconel, I mean, as a partial replacement to Inconel 617 and 625 respectively. Then replacement of Inconel 617 by 740 for boiler tubes. We didn't do it as a part of this project, but that is a plan. replacement of Inconel 617 by Inconel 740. Again, that's a plan for the mainstream piping. Now, these are photographs. I'll show the photographs later. I think these are the smaller versions. I'll come to them now. There were several global firsts, and some of them I have already highlighted here. The first bullet I've been telling, second bullet is well known. Now, state-of-the-art design completed for the first time for a steam turbine in India. Now, design review of boiler and turbine and valves was done by external experts, EPRI and GE and Siemens, sorry. Manufacturing technology at industrial scale was established for the turbine, the boiler, the piping and the valves. Now, these photographs will show all that. I'll come to the photographs later. And this R&D in no way, by the way, was the typical R&D we think of at the lab scale or the pilot scale or even at the demonstration scale. Now, these components that you see on the right were made at 1:1 sizes, were duly tested at whatever standard that were available, and were certified to be withstanding all the tests as per the standard. So it was a little, in fact, a way beyond R&D for that matter. Now, indigenous production of nickel-based alloy tubings, forgings, and the world's heaviest casting. Now, the world's heaviest casting was done by the Central Foundry and Forge plant of the BHEL in Hyderabad, in Haridwar. And we were all there, by the way. I mean, the casting, when it was got out of the furnace and submerged in water for cooling, we had seen that ourselves. And the bottom thumbnail on the bottom row, left-hand side, you can see that it is the world's heaviest casting in nickel-based alloy 625M by the BHEL. And there are several other firsts. I've listed some of them here. As we go along, the design approach, of course, I've been talking about this. Experimental design validation in challenging design areas like turbine rotor, all these things were done. And finally, economics, this was also looked at. I mean, scientists are often blamed for not looking at economics, but we did that as well. And we reduced the content of nickel-based alloys by opting for suitable designs, and though not being, I mean, although it's not being deployed in the country, but we have done that. And bimetallic welded rotor encasing I've already spoken about, where we are retaining 10 chromium to take care of the heavy expenditure on 617 and 625M. Now, these are the tube weldings. The various photographs show the butt joint of Super 304H copper with alloy 617M. Then we are looking at the cold bending of alloy 617M tubes for the given diameter. Then we are looking at the hot squeezing of alloy 617 tubes and the cold swaging of alloy 617 tube. Now, all this work was done primarily in the IGCA and the BHEL Trichy, and part of it in corporate R&D of the BHEL in Hyderabad. And a few other units. For example, there is a piping unit of the BHEL in Thirumayam, if I remember the name correctly. Not very close to Madras, but that is where we take the road journey from. So they have a piping unit there, and the bending of pipes was done there as well as in the Trichy unit. Now, this is the bending of Inconel 740 tubes, and the size is given there. And now this is the welding of Sanico, which is similar welding on the first side. Sanico being welded with alloy 617M and Super 304HCU. And this entire bimetallic or trimetallic welding process was established and tested for the strength of the weld joint. Now, GR91 membrane panel, which goes into the AUSC boiler, was also made indigenously using alloys GR91 and parts of alloy 617M. This shows the manufacturing process as it is going on in Trichy. Now, this is the superheater header of the boiler. Now, while the boiler is made of traditional material, the header, since it would capture the advanced ultra supercritical steam while it is exiting from the boiler, needed to be in the alloy 617M material. So as you can see, I mean, I hope this works. So here the header pipe has been through stub welding, it has been joined to the main body, and the alloy 617M mock-up with superheater header welding is shown here. And of course, the header to header weld and the header to end cover weld is also shown here. And while we made the superheater header in actual sizes, It frankly did not help anyway because the project is yet to see the light of day. Now, this is the Thirumayam. Yeah, that is the name I remembered, fortunately. So there is the pipe bending unit in Thirumayam of the BHEL. And now you can see that pipe bending was being done incrementally in the photograph on the right-hand side. And the diameter is fairly huge. I don't remember. I think it was 14 mm. I don't know. And here we can see this is the pipe bending machine that was used to establish the pipe bending technology. And the bending properties that were established were extra DOS temperature was 1050, the intra DOS was 1080, and the bending speed was a fairly high 3 mm per minute. Now, this is the turbine bypass valve. I mean, as we all know, when you have to shut down the turbine in an emergency or otherwise, we allow the steam not to go into the turbine, but allow it to exit through the bypass valve. Now, this also had to be in the alloy 617M material. It was done, and all its testing, including the hydraulic testing, was successfully established in Trichy. By the way, all these units, if any of you happen to visit Trichy, BHEL or BHEL Haridwar, or even corporate R&D of BHEL in Hyderabad, all these components are still there, and you can see and feel them for yourselves. Now, safety walls, of course, were an important component, but they were successfully completed again by BHEL, the superheater safety valves. Now, the welding equipment, there was a special welding machine that was purchased under the project out of the 900 crores that came from the government of India. And this was established in BHEL Haridwar. So here you see the welding of the rotor, and on the same way, the welding of the casing had been done. This is the first weld of the IP turbine rotor. And now this is the casting that I was talking about. We had taken this photograph and we were there in the shop. So this is a 20-ton finish weight casting, and it is alloy 625M, and it is being submerged in a water tank for quenching. So and this is a kind of a world record. No one has ever done this size ever, and they did it successfully, by the way, without any cracking or without any other materials related problems. Now, these are the turbine blades. The other important thing which was accomplished by the BHEL Haridwar. Now, the blade material came from Medhani, and the machining of these blades, which you see on the right-hand side, these are the turbine blades, was done in this 5-axis CNC machine, which was again purchased under the project. And the BHEL had 3-axis and 3.5-axis machines. They didn't have a 5-axis one, so this was, and you can see that a blade is loaded here. And by the way, from 4 hours per blade, we were able to reduce through this new machine the machining time to, I think, hardly 30 minutes per blade, or maybe slightly more. I don't remember the figure now, it's been a while, but it was in that. It was definitely less than an hour. Now, this is the test loop which was set up in the Dadri unit of the BHEL. And this was a 210 megawatt thermal power plant. And the loop, as you can see, was constructed specifically on a design given by the IGCAR. And of course, the construction was done by the BHEL Trichy. And you can see the loops. There are 4 loops here. And each of these were exposed to the steam that was coming from the boiler off. A part of the steam was taken out from the boiler, and it was fed into the steam pipes. And of course, it was pressurized, and the temperature was also increased to advanced ultra supercritical parameters. And there was no degradation. And I mean, degradation with the time is fine, but there was no untoward degradation which was not designed for. And it was established that these materials can as well function in a real power plant atmosphere as well, other than in the lab, that is in IGCAR. Now, this is the turbine rotor test rig that I was speaking about. The HDSTR stands for high temperature spin test rig, if I remember correctly. It is written there, high temperature spin test rig. And while you see it above ground, actually this whole thing went inside. And there was a proper cavity that was constructed in one of the units of the BHEL. And this all went below the ground level. And as you can see, this is the casing that houses the turbine. This is the casing that houses the turbine. And then it rotates at the design speeds. And then all kinds of material properties are tested at that high speed. But of course, I mean, we are yet to do it for AUSC turbine, because the turbine has not been actually made at an industry. It has been made demonstration, biomedical welding, everything has happened, but the turbine has not been made because that needed money, and that kind of money we didn't have. Now, this gives a summary of the AUSC work. It provides a means for better utilization of coal reserves, which I've already submitted to you. It's a very challenging R&D project funded by the government on a mission mode, and it was executed by the BHEL, HDSTR, and NPCC. We say being executed because we still are trying to hold the consortium together, but I don't know for how long. And then it's first of a kind exercise to take up indigenous design based on the task completion in progress. There is confidence that the project will demonstrate the desired level of confidence on both design and manufacturing by March 2020. But finally, it got a little delayed. It ended in 2021. Now, the lessons learned are obvious. We were able to establish that in India, not only are we able to design, but we are also able to manufacture important components of a 800 megawatt electrical AUSC technology-based thermal power plant totally indigenously, with absolutely no help from any country, any consortium. In fact, we were approached by the US consortium. This I forgot to tell, and this was about the time when we started the R&D. News spread that India is working on the AUSC technology, and the US consortium, which is based in Ohio, they approached us because they had a problem of not having the power plant available for testing at high temperatures and pressures. They were developing the Inconel 740, and they wanted to test Inconel 740 in a real power plant. Now we have the power plants here. The US doesn't have them any longer. But then, of course, I mean, as Dr. Chidamam used to say, we need to leverage international cooperation. It has to be a win-win situation. So we had nothing to win from the US consortium, so that didn't go ahead. Now, the other important point which we were able to demonstrate was that the design withstood the scrutiny by world leaders like Siemens and EPRI. And in fact, they were very appreciative of the work done. Of course, they had quite a few critical comments which were taken care of. And the designs were gradually included. Yeah, so now this is the last, and I'll not go through the other slide because they are a justification for the 800 megawatt electrical AUSC technology-based thermal power plant. Now, these we have put together only to convince the powers that be that why we should go in for the AUSC and why we should not continue with the running after RE full-time or running after any other alternate energy full-time. So if there are questions, I can definitely answer these questions. These are quite a few slides that we put together. Now, this is a cost-benefit analysis. This is the last portion. Due to reduced carbon dioxide emissions, this was done by the BHEL, and they have simulated various scenarios. Now, as you can see, the table shows the estimated project cost with current day prices, the coal consumption, and the CO2 emissions. Now, this is the supercritical, which has been taken as the base power plant. And when you replace it with AUSC, you reduce coal by 11%, you reduce CO2 emissions by 11%, and the estimated project cost is 12 crores per megawatt. But that is a little on the higher side. We have been a little generous in estimating that cost. So ultimately, we wanted the business model to include 6 crores per megawatt from the NTPC, like they do for any supercritical power plant, and the balance 6 crores coming from the government of India as a grant. So 6 into 800, we are looking at a grant of 4,800 crores from the government of India. Now we are talking about 25 gigawatt replacement, 50 gigawatt replacement, and 100 gigawatt replacement. Now AUSC can as well replace all the old thermal power plants that have come to the end of their lives and that are extremely polluting, by the way, and are highly inefficient. So AUSC can be used to replace the current plant. If you don't want to go in for newer ones right now in a big way, we can use this technology to replace the existing ones. And of course, this is the emission trend, which is obvious. The emissions come down with the AUSC replacing the supercritical sets. And thank you for your kind attention. That was the last slide. So let me stop sharing. Should I stop sharing or should I leave this on?
Yeah, you can leave it there.
Okay. Okay. So I hope I have kept myself in the time. It is 6 p.m. So
Yeah. Well in time.
Yeah. So I look forward to questions. I'll try to answer them to the best of my abilities, but if I'm not able to do so, I'll come back to you with answers. Yeah. Some of those answers will be there with IGCAR, NTPC, and BHEL, and not me. Yeah.
Raman, you will take in the questions?
Yeah, I was looking at the chat window, but I have not found any questions right now have been posted. So I open the forum to the audience. Anybody would like to direct any questions at the speaker?
Ramurthy, can I ask some question? Manchanda here.
Yes, sir. Please go ahead, sir.
Sinani, very nice
Ji.
talk actually. My name is Manchanda.
Ji,
I am one of the office bearers of Indian Nuclear Society.
namaskar.
This is the first time I have heard any talk on this area.
Yeah,
My background is, of course, chemistry. First of all, of course, congratulations to you for participating in first of its type technology developed in India. That's what I understand from you.
yeah,
Even worldwide also you said there are hardly any groups who are working on this. It is
Right.
also musical to hear that you have projected nuclear component to go up in the years to come from
Yes.
6% to
Yes.
16%. So
Yes.
very musical to hear this comment.
Yes.
My question basically relates to, you have given the comparison of these materials which are required for this AUSC technology.
Right.
But end of the day, whether this technology has to be integrated, you are very right. So it is aimed at basically reducing the CO2 emission,
Mhm.
but still a balancing act with at what cost?
Mhm.
So what is your real projection that how much it is going to add? I mean, if you leave apart the carbon dioxide emission part of it,
Mhm.
how much this technology is going to cost the company, not the user part, the production
Right.
part, if you
Right.
take unit electricity as one unit actually.
Mhm.
How much it is going to, put the additional cost, 10%, 20%, 5%, any
Well,
idea?
okay. Yeah. So can I answer now?
Yeah.
Yeah. So as I was saying, the capital cost of the plant almost doubles. I mean, from 6 crores a megawatt for a ultra supercritical power plant to 12 crores a megawatt for an advanced ultra supercritical power plant. But we should keep in mind, and all of you are much more experienced and knowledgeable than me, that economies of scale come in only when we start multiplying the numbers. Now, this is the first of its kind plant in the world. And obviously, the prices are going to be high because we are doing it for the first time. There are still some uncertainties that may crop up when we actually start project implementation. So the 12 crores per megawatt has to be taken with a pinch of salt. Now, but to answer your question, the typical price of producing power, now we are being unfortunately compared with solar photovoltaic power. And it stands at about 1.8 rupees a unit now, to the best of my knowledge. And we were kind of cross-questioned by the Ministry of Power that you are talking about almost 8 to 9 rupees a unit, and not price to the customer, but the price of generation. So 8 to 9 or maybe 7 rupees a unit. So how do you account for that? Now to that, I skipped those slides. I've answered that question there. To that, we said that, well, I am from the Department of Non-Commercial Resources. I know that we were considered to be absolute untouchables in the late 80s, 89, 90, 91, early 90s. And our honorable colleagues in the Ministry of Power, the Central Electricity Authority, all utility companies used to kind of laugh on us. When we used to talk about solar photovoltaic power at 18 rupees a unit. That was the price then. Now, how did it come down? It is not just by magic. We did 30 years of development work. Now, some of it was in the lab, some of it was in the industry. Some of this was by learning and then putting back the learning in the process. And after 30 years of hard work, we have come down to 1.2 rupees a unit. But we started at 18 rupees a unit. And that too 30 years ago. Now, if you look at the famous thing that the economists keep saying all the time, the inflation, then that 18 rupees a unit should logically be 50 rupees, 54 rupees a unit today. So we are not being allowed to even set up the first plant and then go on to bigger sizes and more numbers and then come to the final price of electricity generation. Right now, it is, to answer your question, 7 rupees a unit, roughly. I mean,
but this project is now complete, or any more efforts to further
So,
see whether we can reduce the cost further?
No, the project is complete because, a lot of, and by the way, the project took its own while to get completed. We were talking about 2.5 years, but the turbine design part was really tough. And our colleagues in the BHEL Hyderabad didn't know how to design even a subcritical turbine set. So for them to design an advanced ultra supercritical turbine set to produce a final efficiency of 46% was a tall order. So the project ended only in March 2021. The initial time to end was September 2019. So we were extended by almost a year and let us say 6 months. So a lot of hard work has gone already, and we had concluded, we means the consortium, the mission directorate had concluded that nothing more than this was possible in the amount of money that was available and in the time that was available. That is more important, because cabinet approved projects are very strictly monitored, and we had already jumped our timeline by 1.5 years.
Okay, thank you.
Thank you so much, Dr. Manchanda. Thank you.
Thank you. Malhotra ji, I'll come back to you. Before that, a couple of comments and a question.
Yeah.
One question, a comment from Mr. S.A. Bhardwaj, was the former chairman AERB.
Yeah.
Your work is beyond question, excellent developmental work and excellent teamwork between agencies. He compliments you for this. And then there is a question from Mr. Sanat Kumar. I'll just read out the question now. Apart from boilers and turbines and a high pressure turbine relief valve you described, what were the strategies adopted for indigenous manufacture of various individual components such as high temperature relief and control valves, high pressure pumps, special static and dynamic seals that may be required, and various other special process equipment suitable for such high pressure and high temperature applications? That's the question.
Okay, fine. So let me answer that. I didn't cover that because that compared to the turbine design was a little easier thing to do. I just showed one picture of one valve. There was a superheater safety valve that was shown. Now, all those valves have been designed indigenously based on high temperature materials, primarily alloy 617M, and all kinds of valves, including the high pressure bypass valve, which is the big valve, which is supposed to shut down the plant, have been already done indigenously. The complete design, except the manufacture of the AUSC turbine on 1:1 scale, has been completed.
Thank you.
Raman, can I ask a question? Raman?
Raman, you are muted. Raman, you got muted.
Yeah, Mr. Malhotra has already raised his hand before you. So can Mr. Malhotra first ask his question?
Yeah.
Yeah, please, Mr. Malhotra.
Sinha Sahab, first of all, congratulations and my compliments for a wonderful presentation and the wonderful work which has been done by the entire group.
Right.
My compliments to all the contributors.
I'll pass on your good words to all my team members.
I have a query. My query is not in really about this project. Let me declare that my query is outside this project. And I'm asking it because presently you are in Niti Aayog.
Right.
So see, our Prime Minister has already committed net zero emission by 2070. So whatever technology we may develop, there is going to be emission from this plant. Okay. And now net zero means it doesn't mean that nothing will emit carbon dioxide. You can emit carbon dioxide, but then you have to either that carbon dioxide or some other carbon dioxide you have to capture. So that the carbon dioxide emitted by you and captured by you, that will decide whether you are net zero or not. So my question is, what is the work going on or thinking going on in Niti Aayog about carbon capture technology and sequestration technology?
Right. So thank you so much. A very relevant thing you raised. I had skipped this slide because this was the justification part. Now, the Niti Aayog had conducted a national workshop where there were 3 international speakers also on carbon capture, utilization, and storage. And we had looked at all the possibilities, including underground sequestration and fixation in biological formations, and of course, putting carbon dioxide for enhanced oil recovery and for other useful applications without actually allowing it to escape from the chimney. Now, as you see, the various energy scenario analysis by the IEA is talking about India continuing to depend on coal, that to 40%. I don't know how much to believe this in the year 2050. So we have already identified that CCUS without carbon capture, utilization, storage will not happen.
Yeah.
And we have to heavily invest in CCUS to ensure that we are net zero. Otherwise, we'll never be net zero.
Yeah.
The emissions will obviously be there as long as we are generating using coal.
Yeah.
So to answer your question, this is already on the map of Niti Aayog, and Dr. Saraswat is leading it from the front as the member of Science and Technology.
Okay. Thank you.
Thank you.
Ramarao, you wanted to ask a question?
Yeah.
Yeah, please.
Niraj, this turbine that is generated, that is developed,
Right.
was to undergo test on the test bed in BHEL.
Right.
What is the progress on that?
No, that is what I will see. The test bed that you are talking about is the photograph of which I showed.
Yeah.
That is the turbine rotor test rig which has come up in
BHEL.
corporate R&D in BHEL. So there we have already, kind of self-tested the rig using a stainless steel casing. Now, the project, actually, since these two projects, the test loop and the turbine rotor test rig were funded by the DST, they were not coterminous with the main R&D project, which was funded by the Government of India.
Okay.
As you know, the main R&D project ended in, as I just said, March 2021.
Yeah.
Whereas these two projects are supposed to be ending in 2022, if I remember correctly.
Okay.
And we are already talking about sanctioning the phase 2 of that project through the DST, where we are going to actually, test a turbine, provided it is available. We don't have a turbine. No? The AUSC turbine is not there.
Okay.
We need the money to import the material or make the material through Medani.
Okay.
So a huge amount of materials goes into the rotor and it goes into the turbine casing.
Mm-hmm.
So we don't have that kind of money. So hence that work will happen, but only when the government decides to go in for the phase 2. And by the way, Ramarao Sahab, you are aware, we used to call these two components as phase 1 and phase 2.
Correct.
Phase 1 was the R&D, phase 2 was the actual erection and commissioning, as I showed in one of the earlier slides.
Yeah.
Now, both these phases were mentioned in the cabinet note on purpose by us, basically by the PS's office, because we wanted to establish right from day one that there is an interlinking of the two.
Okay.
Otherwise, spending around 1,000 crores plus on a technology and then allowing the design to rot in our bookshelves is a straight misuse of expensive government money.
Correct.
We have used this argument also to wake up some people in the government.
Okay.
But even that has not succeeded. Because this is, frankly, this is a waste of money, right? This R&D was supposed to go into the phase 2. And let me also submit to the gathering here that the phase 2 was the ultimate aim right from day one. It is not that we started doing R&D and then suddenly we dreamed of it in a megawatt. As I said, Dr. Baldevraj had spoken about an 800 megawatt plant right from the day one itself. So it was like a directed basic research, as Dr. Chidambaram calls it. It was directed towards the plant, but it involved a lot of basic research.
Yeah.
So, so that doesn't happen until we have the money.
Yeah.
That is our problem.
Yeah. Thank you.
And otherwise, the test rig is there, and I will request all of you, if any of you are incidentally in Hyderabad, Trichy, or Haridwar, please let me know. I can organize your visit to these units, and I'm sure the people there will be as happy as you.
Yeah. Thank you. Thank you.
Thank you.
Mr. Bhardwaj would like to comment, sir.
Yeah.
Please.
Yeah, Dr. Sinha, it was excellent to listen to you. Great success in the country. Mike, one day AUSC will happen. I think after this summer itself, it will be realized that we have to save coal and also have coal plants. So it will happen.
Thank you so much for that. Golden words.
My question is, we have for the first time developed capability in the country to design a turbine.
Right.
To design, steam valve and so many things.
Right.
This should have a fallout. And nuclear power today, we get into difficulty while getting a turbine for our plants.
Right.
Because there are tie-ups with the companies who are reluctant to give it to nuclear plants. We have a lot of difficulty with Alstom and Siemens. So why not now use this capability which has been developed? Of course, it has been developed for AUSC. So you have to come down to saturated turbine.
Right.
But I think this group should continue to provide these fallout services of design for Indian plants, and nuclear is one. Similarly,
Right.
very fast-acting steam discharge valves we are still importing. You know,
Right.
total nuclear plant we are importing some equipment for secondary system, which is
Right.
painful. You know, we are all making all nuclear components in India, but
Hmm.
we are buying some valves and something for these steam.
Hmm.
And now with this capability available and the team available, I think we should have a phase 3 or call phase 2 dash
Right.
to use the fallout of the capability developed in the country. So
No, I see, Dr. Bhardwaj, I couldn't have agreed with you more. In fact, this was the line which was adopted by Dr. Balderaj and Dr. Chidamam also long ago. In fact, there was a group that was set up to look at why are we still importing steels that are used in the manufacture of subcritical and ultra supercritical sets. I mean, having designed material and having demonstrated material, having manufactured material for advanced ultra supercritical parameters, why can't we do it for 560 degrees Celsius and around 240 bar pressure, which is the typical supercritical condition of steam? So that group unfortunately kind of faded when Dr. Balderaj left us, and we wanted Mr. Chetal to carry it forward, but that didn't happen. And we had involved quite a lot of stakeholders in this. Tata Steel was there, and of course, Dr. Balderaj was chairing it, and scientists from atomic energy, space, and defense R&D were there. And we had these private companies, Bhushan Steels and Strip, which is a part of Tata Steel now, as members. So everything is possible. The only thing is to get people together. Now, my own personal handicap is that although I'm still a PSS office person, but I don't work there any longer. I'm on deputation to the Niti Aayog. And with Dr. Chidambaram having left in 2018, Dr. Vijayaraghavan, of course, carried it forward very aggressively. But now he's also kind of demitted office. So there is a kind of a lull. I mean, you need aggressive leadership for taking anything forward. And why I complimented everyone, all my seniors before starting this presentation, we owe it to them. We owe it right from Dr. Chidambaram to Mr. Chetal for having led this from the front. Otherwise, it wouldn't have happened. So the leaders for the remainder part of the work are not there. The PSS office, for some reason, is not taking it up any further. Niti Aayog, unfortunately, can only advise. By the way, the Niti Aayog played a very good role. I missed this part. I think it was there in the justification part. See, way back in 2019, when I had just joined Niti Aayog, the Ministry of Power had developed a project investment board memo. They call it a PIB memo, if I remember the name correctly, wherein they were talking about Ministry of Power investing about the amount of money that we want, about 5,000 crores of rupees to build the phase 2. And there was a PIB memo that when generated went around for interministerial consultation. It might have gone to the Department of Atomic Energy as well. When it came to Niti Aayog strongly supported it. And both the then Vice Chairman, the CEO, Dr. Saraswat, and of course, I was there to support it. We strongly supported it. We said that this is something that India should do. But even then, it doesn't happen. Because, what happened was, unfortunately, the turbine design did not get completed by September 2019. And the then Secretary Power said, Baba, complete the design first, and then we will look at the PIB. Because, leadership changes. The then Secretary Power became the Home Secretary. Even today, he is the Home Secretary, Mr. Bhalla, Mr. A.K. Bhalla. So he had led it very strongly. He said, don't worry, Sinhaji, and I am going to get a PIB memo generated, and we'll take it forward. But then he got kind of promoted as Home Secretary, and then things took a downturn. So this is the way, unfortunately, the administration or the management of R&D happens in India. And this is unfortunate. And it is a real dampener for all the scientists and engineers that are working overtime throughout India to realize technologies. The hand is extended, there is no one to catch the hand. But we are still trying. Yeah, we are still trying. We are not giving up. Dr. Saraswat, myself, Dr. Vijayaraghavan, and the new PSA, Dr. A.K. Sood. We are still going to get together and give a presentation, God willing, to the PMO and to the PM himself if possible. But this is something which I don't want to talk about more because it's yet to happen. But in the interest of the country, it is important for us to make people sit up and take notice. And it was thanks to the PM that the phase 1 got sanctioned by it. Even that was finding it very difficult, but thankfully the PSA spoke to the PM and it got sanctioned. thanks to the PM's foresightedness. It happened, and we were able to accomplish this much. So, I mean, frankly, I couldn't have agreed with you, Dr. Bhardwaj, more, but there is no one to actively involved to carry this forward. Niti Aayog will still do it. We are still trying hard, and we'll keep all of you informed.
Thank you. Keep trying, because this is very
important. We will not give up. We will not give up.
Behind this.
Yeah. People like Dr. Saraswat and Dr. Vijayaraman don't give up. So we won't give up.
Thank you, sir.
So,
Malhotra ji, you wanted to join in now?
No, I asked already. So
Okay.
now, whenever you decide, I will propose a vote of thanks. That's all.
Yes, sir. You now propose a vote of thanks.
Yeah.
Okay. Thank you very much.
Thank you.
So first and foremost, Neeraj Sinha ji, thanks a lot, both on my personal behalf and on behalf of INS fraternity, for a wonderful talk. And yes, I do agree with you. You all have developed this technology, and definitely you will be looking forward, and along with you, people like us also will be looking forward that this is put to use. It doesn't, as you said, doesn't remain in the bookshelves. So all the best for that.
Thank you.
And once again, I thank you for the talk. And just now, you know, I was feeling a little bad that you were exhibiting some helplessness. But
Yeah.
I tell you, you will know this information, but let me reiterate that even the present PSA, he is basically, to start with, a DAE person.
You know,
And,
IG car.
And from IG car. So I am 100% sure that when you tell him about the develop, that it all started from IG car,
Yeah.
I think he will show equal dynamism and equal leadership.
I'm sure.
And I wish you all the best for that.
Thank you. Thank you so much.
Yeah. And now next to that, I thank our president, respected Mehta Saab, for leading us, continuing to lead us. And I thank all my colleagues in the executive committee of INS for continuously interacting and showing us the path wherever required. I particularly thank Dr. Ramarao. I was not knowing, since actually I got educated today, I was not knowing that Dr. Ramarao was involved in this project. So in fact, I was wondering how did he reach you?
No, it was through Mr. Chetal, if I remember correctly.
Oh yeah.
So Dr. Ramarao, it was through Mr. Chetal. I mean, that's
Yeah, through Chidambaram, in fact.
Oh, through Dr. Chidambaram. Oh, you're right.
Yeah,
yes, through Dr. Chidambaram. Yes, this was.
I thank Dr. Ramarao, particularly not only for arranging webinars in general. So of course he has done his duty for arranging the 21st webinar. But in addition to that, especially when he brings experts and technocrats from outside DAE, and so that, you know, we don't remain the frogs of the well. We also know that outside the DAE domain, what all is going on and what other technologies are being developed. So thank you very much, Dr. Ramarao and his team. And then, of course, I am thankful, which I always mention, I am thankful to our treasurer, Shri G.D. Mittal, and our colleague from BARC, Mr. Shimjit Rajgopal, who contribute, you know, in propagating the information about our webinars, making reach the message across the community so that they can join. And now with, in fact, we keep on debating whether we should give live feedback to the YouTube. See, because once we give live feed to the YouTube, we don't really know how many people are watching us or how many people are actively going through the webinar. So I think we should have a rethink on that. But on that note, I thank all the audiences whose numbers we could see here. And in addition to that, I'm 100% sure multiplied by some number must be present in on the YouTube. I thank all of them. And usually I thank my vote of thanks by giving information about the next webinar. But the question paper is not totally leaked out to me. So though I know the name of the speaker, but I don't, I think the topic has not been decided. So let me keep my fingers crossed. So we will let you know when is our next webinar and who will be delivering and what will be the topic. Till then, good evening. Enjoy your weekend and enjoy the week ahead also. Thank you very much. And Neeraj Sinha ji, thank you once again.
Thank you
I
so
take
much.
leave.
Neeraj ji, thank you. Thank you.
Yeah,
Neeraj
thank
ji.
you. Just
Thank you very much.
one thing I wanted to add. I have an umbilical cord attachment to the DAE.
Yeah.
My father is from the second batch of the training school.
Oh,
58,
what's his
59.
name?
So that's how I know everyone's batches. I know that Dr. Sood is from the 15th batch. So, and Dr. Baldiraj was from the 13th batch.
Yeah.
So that umbilical cord attachment will remain. Always.
Yes.
No, so what is the good name of your father?
Mr. P.S. Sinha, Mr. Prem Shankar Sinha. Actually, he was in the electronics group, and then Mr. ASO wanted him to work on the famous ADJST project. At that time, ADJST was a strategic project of the government of India.
Okay, okay.
So Dr. ASO took him to ECI. As you know, ASO have shifted to ECI.
Okay, very good. That is how I think we, the BRC guys, we probably, yeah, I mean, at least I have heard his name.
Right. He left in 71. He left BRC in 71 after 13 years.
Yeah.
So that's how it is. But thank you so much. Thank you for having me.
Thank you.
Thank you to all of you.
Thank you,
so
sir. Thank you very much. Bye-bye.
Thank you. Namaskar.
Hi. Shall I stop the recording, Ramaro?
Yeah. Stop there.
Okay. Goodbye.
Bye-bye.